move on to the next, that is a relation between the strain displacement relations. Strain displacement relations. Strain displacement relations. Why we know its displacement components. So once we know the displacement components, because of that reason automatically it will strains whenever we are applying the loads, it will deforms. So for that we need to go back the basics and then we will solve. Now U is equal to formula. What is the formula? U1 V1 plus is that N2 U2 plus N3 U3. This is equation number 1. Here once again we will study. That V is equal to what is that? N1 V1 plus N2 V2 plus N3 V3. Okay. So this is equation 2. Okay. Now the strain, which is the ratio of displacement to length. So in the normal strain in x direction, in the two-dimensional cases, we have an idea. What is that? Strain in x direction, normal strain. Normal strain. These equations already we discussed in the first unit. At the same time, we would be knowing the mechanics of solids also. Strain is equal to what is that formula? Dou U by dou x. Yeah? Dou U by dou x. Normal strain in x direction. Dou U by dou x. Now we know the equation U. What is that? N1 U1, N2 U2, N3 U3. Okay, we know this equation. Next we need to write it as dou N1 by dou x U1 plus dou N2 by dou x U2 plus dou N3 by dou x U3. Equation number 3. What we did, just along its x direction, the normal strain E, or we can say that this simple small e also we can write it as sigma e, whatever. Now at the same time, normal strain in y direction also there. Normal strain y direction. Y direction. What is that? Normal strain in y direction. Strain in y direction is equal to what is that? Dou v by dou y. Yeah, we know the v equation 2. Equation 2, what it say that it is v function in y direction is equal to dou n1 by dou y v1 plus dou n2 by dou y v2 plus dou n3 by dou y. This is equation 4. Okay, these are the normal strains in x and y directions. Because it is a two-dimensional element, obviously in the two dimension there is a shear strain will comes into picture because of this x and y. Shear strain will be comes into picture. So we know that shear strain gamma xy is equal to dou u by dou y plus dou v by dou x. We know that equation. I will move on to the next slide. Okay. What is that shear strain in xy plane? In xy plane. What is that? That is gamma xy is equal to dou v by, or we can say that u, dou u by dou y plus dou v by dou x. So I am writing here that is dou n1 by dou y u1 plus dou n2 by dou y u2 plus dou n3 by dou y u3 plus dou n1 by dou x v1 here. Similarly, dou n2 by dou x v2 plus dou n3 by dou x v3. This is equation, previous slide what the equation number is given, 4. This is equation number 5. Okay, these are the strains in x, y directions of normal strain and shear strain in x, y plane. Okay, then we can write it as these equations in the matrix form. Writing the equations that 2, 3, 4, 5 in the matrix form. Next, I move on to the next slide because here the space is not sufficient. I think so. Okay. You need to follow so the matrix form. Simply just what are the equations are there, that 3, 4, 5 equations in matrix form. We'll get strain in x direction, strain in y direction, shear strain because of the explained is equal to, just what I am trying to write is dou n1 by dou x 0, dou n2 by dou x 0, dou n3 by dou x 0. The same way the second one is strain in y direction, 0, dou n1 by dou y 0, dou n2 by dou y 0, dou n3 by dou y. The final form is, that is dou n1 by dou y, dou n1 by dou x, dou n2 by dou y, dou n2 by dou x, dou n3 by dou y, dou n3 by dou x. Then multiply with, what is that vector is displacement vector u1, v1, u2, v2, u3, v3. This is the displacement vector. Okay, just what we did, simply we can write it as the strain equations in matrix form. What are the equations are there here? These two equations, equation 3 and 4 and equation 5, this equation 5, just we write it as matrix form. So we'll get this one. Okay, now we know the n1, n2, n3 values, n1, n2, n3. Yeah, we know that. What is n1? Shape function. What is n1? Alpha 1 plus
beta 1x
1x plus gamma 1 y divided by 2a.
2a.
Yeah. Similarly, n2. What is n2? Alpha 2 plus beta 2x plus gamma 2y divided by 2a. Similarly, n3. Alpha 3 plus beta 3x plus gamma 3y divided by 2a. These are the shape functions already we derived, n1 and n2, n3. So from these n1 and n2, n2, n3, then we can derivative with respect to 1 in x and y directions. So what is now, what we can say that dou n1 by dou x. What we will get? Dou n1 by dou x. Here in the previous slide, dou n1 by dou x means this is constant, no need to bother about it. This is the y, not related to x. Only beta 1 by, what is that? Beta 1 by 2a.
2a.
Then remaining things, once we will get it, means remaining things we can get it as n2 by dou x. What is that? b2 by simply 2a. Similarly, dou n3 by dou x is equal to beta 3 by 2a. Okay. Similarly, what is that? Y. Dou n1 by dou y. What we will get? Dou n1 means 1 means y plus gamma 1. Yeah, gamma 1 by 2a. Similarly, dou n2 by dou y is equal to gamma 2 by 2a. Another one is dou n3 by dou y is equal to gamma 3 by 2a. These are the its coefficients. Once we differentiate with respect to its shape functions, then we will get this one. Substitute these values. What are the values we get? Then we need to substitute these values in the equation. What is this equation? What is the numbering equation given? Sixth equation. Okay. Substitute these parameters in the equation 6. And then what we will get? Strain in x, strain in y, shear strain xy is equal to 1 by 2a, because 2a is common in all the parameters. 2a is there, 1 by 2a, area of that matrix. Beta 1 0, beta 2 0, beta 3 0. Similarly 0, gamma 1 0, gamma 2 0, gamma 3. So the final one is gamma 1, beta 1, gamma 2, beta 2, gamma 3, beta 3. Multiply with, what is the displacement vector is? u1 v1, u2 v2, u3 v3. Equation number 7. Okay. Now, from the basics of the previous classes, there is a strain displacement relation. Okay. That relation matrix, you might be recollected. What is that? Strain is equal to B into some displacement vector. Yeah, do you remember or not? Strain is equal to some B matrix multiply with its displacement vector. Yeah. In the first, second unit and third unit we discussed like that one. strain is equal to some matrix, okay, multiply with displacement vector. Now that is the strain displacement matrix, or we can say that gradient matrix. Now here in the same way we can write it as strain is equal to B multiply with delta. Strain is equal to B multiply with delta. Although delta means what, we can say that this is the displacement vector. Already we know that is u1, v1, u2, v2, u3, v3. Okay. Now strain means the strain vector is in x direction, y direction, and shear strain in x vector. That is, the next one is B matrix, the strain displacement relation matrix. That B matrix is, what is the B matrix? 1 by 2a. That is, we can write it as, what is that B matrix? That is important, B matrix, because if you want to calculate the stresses and stiffness matrix, we need to use this B matrix. So 1 by 2a multiply with, what is the B matrix? Beta 1 0, beta 2 0, beta 3 0, 0 gamma 1, 0 gamma 2, 0 gamma 3, gamma 1 beta 1, gamma 2 beta 2, gamma 3 beta 3. This is the strain displacement relationship matrix. Okay, this is the strain displacement relationship matrix. Okay, strain displacement relationship matrix. Now then you know the what is beta. Then for timing I am asking, what is beta 1? Beta 1. Betas or gammas are, beta is with reference to its y direction, and gamma is with reference to its x direction. You can remember like that. Beta 1 means y2 minus y3. y2 minus y3. Okay. What is beta 2? y3 minus
y1.
y1, yeah. Beta 3 means y1 minus y2. Similarly, gamma is also, gamma 1 means x3 minus x2, gamma 2 is x1 minus x3, gamma 3 is equal to x2 minus x1. These things already we discussed, just was trying to recollect it. Delta means displacement vector. Okay. So once we know this, then it is easy to solve the, or we can easily to derive the stress displacement relations. Stress displacement relations. Stress. This is the previous. This one is strain displacement relation. Yeah, strain displacement relation. This one is. And I will try to conclude within two minutes. Just to see that stress displacement relations. Stress displacement relations. From the basics, we have an idea. Stress is equal to, what is the formula? Stress is equal to, initially I told you, I already explained, D multiply with strain. This equation we might be know that. Means stress is equal to, what is the formula? Young's modulus multiply with strain. Yeah, this we can easily recognize. Stress is equal to Young's modulus multiply with strain. Did you get? Whenever I am asking the questions, you, at least anyone can answer. Why? Because whether my network is connected with you or not, I don't know that. That's what I used to ask the questions. I have doubt. People are connected or not. be connected, but no one is answering. This thing we know that stress is equal to Young's modulus multiply with strain. We know these equations. Mechanics of solids, not only that, many of your subjects we are familiar. Now this Young's modulus means material property. That for one dimensional case directly we can substitute as this one is okay, but if you go for the two dimensional, three dimensional, that material property matrix will comes into picture. That is called D. What is this one is D is material constitutive matrix. We can say that simply. We can say that for simplicity it is material property matrix. Material properties matrix. Now we know that stress is equal to, this one is D, means material property matrix or material constitutive matrix, multiply with B multiply with delta. Yeah, what is this one is D, I will tell you. B we know that, yeah, B we know that already, just now we derived the B matrix, that is relation between the strain displacement relationship matrix, that is B matrix. That B matrix we know that means its displacement vector like u1, u2, v1, like that, three components are there. Because of that reason these things we know that. Only unknown is this D. This D also we know that we derive the plane stress and plane strain conditions. Plane stress and plane strain conditions. That condition has to use it here. Now we'll go on to the next slide. The stress in x direction and the stress in y direction, shear stress in xy direction. Stress matrix is equal to that is D matrix. What is D matrix is, here we are using the plane stress case. Okay, plane stress case. In plane stress, just I am writing plane stress case. There are two conditions are there, plane stress and plane strain conditions in two dimensions. Just I am using the plane stress condition. Young's modulus divided by 1 minus mu square multiply with 1 mu 0 mu 1 0 0 0 1 minus mu by 2. I think then you can recollect it, this one. This is the, what is the, this one is the D matrix, material constitutive matrix. Multiply with, what is that? You know that 1 by 2a. That formula is beta 1 0 beta 2, because it is B matrix, 0 beta 3 0 and 0 gamma 1 0 gamma 2 0 gamma 3, and always gamma 1 beta 1 plus gamma 2 beta 2 gamma 3 beta 3, multiply with, what is it, u1 v1 u2 v2 u3. Okay, this is the strain displacement relations, or we can say that stress strain relations also. Okay, now this is the way we need to get it. If you multiply with this matrix, what we will get? Because this is a 3 by 3 matrix and this one is 3 by 6 matrix, and finally what we will get? 3 by 6 we will get. 3 by 6 we multiply with this one. What is this matrix? This one is 6 by 1 displacement vector. Then it is cancelled. That we will get the 3 by 1. So like that. Here the, for understanding purpose I am explaining these things. Matrix simplifications. Okay. These are the strain displacement relations. Once again I am repeating here, the D matrix is the plane stress case. Already you know the plane strain case. Plane strain. So if you they ask the condition in two dimensions, use plane stress and plane strain. According to that we have to use that D matrix.